Okay, so our next speaker is Ben Hoare, and he will tell us about integrable sigma models and the string worldsheet.
That's great, thank you very much. So let me start by thanking the organizers. It's a great pleasure to be here, my first time in Padova. So what I want to tell you about today is some work that's been going on, I guess, over the last 20 or more years, depending on how you count, on these integrable sigma models and the string worldsheet. And in particular, much of what I say, this is my perspective on 20 plus years of work, and many people were involved in this. I haven't included citations because they would probably just fill up the slides. So please forgive me for that. I'm very happy to provide references for anyone who is interested. Okay, so I'm going to start with possibly the slide with the least content in this conference. That's our starting point. So we're considering closed strings moving on curved spacetimes. And in very simple examples, if we consider a string moving on a sphere, we can rotate the sphere, and this system will have a global SO3 symmetry. But the dynamics can also be constrained by infinitely many hidden symmetries, and these act non-trivially on the string, and in this case we say that we have an integrable sigma model. So this is the topic of the talk. So let's see if this works. So this is obviously the string moving in target space, and then we have this description in terms of a cylindrical worldsheet, and then a two-dimensional theory living on that worldsheet, and that is going to be this integrable sigma model. So just let me give a little bit of motivation. Why am I interested in integrability? So as I've already said, there's a large hidden symmetry at the classical and quantum level. We've heard some of this before already, but it gives us access to all values of the coupling. It allows us to conjecture exact results that can be precision tested. And something that will come up again and again is this idea of controlled deformations or dualities. But by controlled, what I mean is you do a deformation or a duality that preserves some symmetry or some property that you want, and in this case that will be integrability. So why string theory? Well, as we've heard many times, it's a theory of quantum gravity, one of the theories of quantum gravity that we have the best control over, and it also gives us insights into gauge theory through gauge gravity duality. And finally, why integrability in string theory? So it actually gives us a new approach to solve strings in non-trivial backgrounds. If we have Ramon-Ramon fluxes, then typical worldsheet CFT methods are not easily applicable. And then moreover, it actually provides us lessons for solving integrable sigma models more generally, and these have applications beyond string and gauge theory. So I'm going to start probably about, I think probably about 2002, 2003, and just recap a bit the methods that we use to study integrable worldsheet sigma models. So we're starting from a free closed string propagating in a curved spacetime, and the sigma model on the sigma model on the cylinder is classically integrable. It has this infinitely many hidden symmetries, and these are encoded in a lax connection. No, that one. There we go. L, and it depends on a spectral parameter, an auxiliary spectral parameter Z, which is valued in C. And from this lax connection, we can construct a which is the path ordered exponential of the lax around this curve. Nope, this is not working. Around this curve, around the worldsheet. And by expanding the trace of this monodromy, it's easy to show that it's conserved in time, and by expanding this in powers of the spectral parameter, we construct infinitely many conserved quantities. So then the story goes on, and you fix a uniform light cone gauge. So this is a type of gauge fixing on the string worldsheet where we eliminate all unphysical degrees of freedom. So generalization of the usual light cone gauge of flat space to curved space. And we expand around a point-like string solution. What we end up with is a two-dimensional integrable field theory on a cylinder with 8 bosonic and 8 fermionic degrees of freedom. That's our usual degrees of freedom of worldsheet string theory. If we have curved spacetime, then we often end up with interactions that are not Lorentz invariant. And the global symmetry of our model will be broken to a subgroup depending on the particular light cone gauge that we picked. So then, just to rapidly move through probably about 5-10 years worth of work, the story goes that you decompactified the string worldsheet, so you're now considering your theory on a plane. You consider excitations, and you scatter these excitations, and using integrability, you can conjecture, and various other physical properties, you can conjecture the exact dispersion relation in the S matrix. In particular, you can use the Yang-Baxter equation, which is basically saying your multi-particle scattering factorizes into two-particle processes. And once you have this S matrix, you can develop and use the integrability toolkit. So there's various methods which we've heard mentioned briefly, asymptotic beta ansatz, thermodynamic beta ansatz, quantum spectral curve, so on, to recompactify the string and conjecture the closed string energy spectrum. So we've already kind of heard hinted that I'm only telling you one half of the story. I'm only telling you about the strings on ADS space, and one of the motivations for studying this was the ADS-CFT correspondence, and in particular the ADS-CFT correspondence is challenging to test or prove. It's a weak, strong duality. Solving strongly coupled conformal field theory is different, and strings on ADS space need to be supported by these background fluxes, which means we can't use these worldsheet, or sometimes we can't use these worldsheet CFT methods. So integrability provides us with a way forward, and I'm just checking. I think my triangle is the same orientation as Zolli's. We have CFT in the top left, and we have string theory in the top right. In particular, we're in the planar and free limits, so the free string limit corresponds to this planar limit in n equals 4 super Yang-Mills. And we have an underlying integrable system that describes both of these theories. And this triality has sort of led to many remarkable achievements. As I briefly mentioned, it's led to a proposed solution for the spectral problem for all values of the coupling. It's grounded in rigorous string theory and CFT, by which I mean you can precision test this on both sides of a strong and weak coupling. And it's a remarkable new successful application of integrability methods. However, there are some big open questions. I think it's fair to say that ultimately quantum integrability is a conjecture. So we can test this at weak and strong coupling, but in principle, we should prove that these theories are quantum integrable for all values of the coupling. The underlying hidden symmetry is not well understood. So for example, on the CFT side, I didn't really mention this, but the integrability manifests itself in a spin chain, which we did hear about yesterday. And that spin chain is known at small values of the coupling, but it's not known to all orders in the coupling what this spin chain actually is. And ultimately, it's most successful for the most supersymmetric cases. So I'm mainly going to focus on this last point and ask the question, how do we move away from 32 supercharges? So ADS5S5 is this example of this maximally symmetric background with 32 supercharges, and we want to move away from this. And this is just a selection of kind of approaches that people have been using. Now probably we're in the last decade, a little bit more, to tackle this question. So there's a kind of, I flipped the orientation of my triangle, but there's a kind of, there is a triangle here. We have sort of worldsheet deformations and dualities. So this approach is sort of starting from the string sigma model and asking how we can deform or dualize or modify the string sigma model to preserve integrability. In the top right now, we can look at CFTs with less supersymmetry and ask, can we find integrability or the effects of integrability in those theories? A third approach is to start from the integrable structures themselves, for this scattering matrix on the worldsheet theory of the string, and try to deform that model, or try to deform that itself. Another approach which we heard about yesterday, which I won't mention anymore, is to consider things like defects, orbifolds, and boundaries in your theory. And then the final thing is to try and go down to lower dimensional ADS backgrounds, so ADS4, ADS3. So mainly today I'm going to focus on these two in the top left as you're looking, so the worldsheet deformations and dualities and the lower dimensional ADS backgrounds. So let's start with the lower dimensional ADS backgrounds. As we go down in dimension, there's been various classifications that have been carried out, and we find more and more integrable string sigma models with less and less global symmetry. So in particular, if you go down 1 to ADS4, you find ADS4 times CP3. If you go down, one option is ADS3 times S3 times T4, but you could replace the T4 with S3 times S1. There's a moduli space for this theory. You can support it by different fluxes. So new features appear as we go down in dimension, which is appealing. However, also the lack of global symmetry, or the less global symmetry, means that we have less immediate control. We have more objects that we can play with that are invariant under these symmetries. So that's one direction. The other direction is to look at deformations and dualities. And this is a very cartoony sketch of the landscape of deformations and dualities. I'm not going to go into it in detail, but basically there's a kind of myriad of possible ways to deform and dualize, and they break different amounts of symmetry and supersymmetry. And for those of you who are familiar with sort of quantum integrable systems or integrable systems, these deformations include the sort of sigma model avatars, if you like, of Drimfeld twists and quantum group deformations, Q deformations. So this beta gamma deformation is an example of a twist, and these eta and lambda deformations are sort of correspond to Q deformations. And moreover, we can sort of generalize T-duality to non-abelian and Poisson-Lie symmetries. And I guess the message I want to take away is this is a big space of models. So when we put it all together and we go down in dimension and we kind of expand out to all these deformed models, we end up with a kind of really big landscape. And one of the kind of main things that's been kind of achievements over the last few years is kind of understanding this landscape in a more systematic way. So I remember being told probably about 5-10 years ago that which deformations, or asked the question, which deformations should I care about? There's too many of them, I can't study them all. And it was a very good question, and I think we are slowly starting to pin down which are the interesting cases and sort of understand this landscape and how they are related to each other. So at this point, I have sort of 3 slides of kind of directions / questions that I think are interesting in this landscape and beyond. These aren't sharp questions. I'm very happy to give people sharp questions. There's many of them I would like to answer, but these are sort of areas which I think if someone could say something interesting about these, it would be important. So let me start just with integrable string theories and charting the landscape of and solving integrable string theories. So a kind of question that has received a partial answer is, do we always find consistent string theories? So if we take a model, I'm talking about deforming or dualizing while preserving integrability, that doesn't necessarily guarantee that I preserve Wahl invariance or string theory, or that it gives me a consistent string theory. So there are kind of different aspects to that question. One is whether the theory is Wahl invariant itself, and that question has received has a kind of pretty solid answer. We know when it is and when it isn't. There's another big question, which is that many of these backgrounds end up having singularities, essential singularities in the curvature, and as far as I am aware, it's very unclear how to treat these singularities. So my approach to that question is to look for models that don't have singularities, but there are ideas about how to interpret these singularities themselves. When we deform, when we dualize, we break symmetries. Uniform light-cone gauge fixing relies on having certain symmetries. Can we follow this integrability path of fixing uniform light-cone gauge and constructing the S matrix? How do the symmetries interplay with the S matrix itself? And then can we go on further and apply all this toolkit, this ABA, TBA, quantum spectral curve? So I should say that for different models, some of these questions have been studied, some have not, but there's bits and pieces of kind of information in all these directions, and there's many kind of open questions. And then finally, something that was discussed in Zoli's talk, so can we move beyond free strings? So beyond just the spectrum to correlation functions or even higher genus. There's a whole bunch of special limits that we would like to understand. So one that's received a lot of attention is ADS3S3 T4, where you can support the model just by pure NSNS flux, and how, in that case, you can use normal worldsheet CFT methods, and how the integrability approach maps onto that. Flat space limits, tensionless limits, non-relativistic limits we heard about this morning. There's also a whole bunch of different formalisms. So we have the Green-Schwarz formalism, pure spinor formalism, hybrid formalism, and it's an interesting question how all of these are related. Can turn now to sort of the gauge theory jewels of integrable string theories. So what are the gauge theory jewels of lower dimensional ADS backgrounds? For ADS5 and ADS4, we kind of know it's n equals 4 and ABJM. For ADS3, there are certain points in the moduli space where there are good proposals, but moving away from those related to the symmetric product orbifold, moving away from those points, there's kind of questions to be answered. So that's lower dimensional ADS backgrounds. We can also ask about gauge theory jewels of deformed backgrounds. In this case, there are kind of two approaches. One is to take the spin chain that you get from n equals 4, for example, and try and deform that spin chain. You could also try and deform the n equals 4 Lagrangian itself, and in this case you get sort of non-commutative field theories appearing. And then there's some, I think, very interesting questions about certain limits that you can take in the gauge theory. What is the string theory interpretation of that? And let me just focus on the middle case here. So that if you take n equals 4 super mils and you do sort of a twist of this model and you take a maximal deformation limit, so you take your deformation parameter off to infinity, but at the same time you take the Yang-Mills coupling to 0, so you do this double limit, you get a very nice model called the fishnet model, which just has two complex scalars, and is meant to be integrable, or it is integrable. There is a proposed jewel for that model called the fish chain, but how you relate that proposed jewel, how do you get that proposed jewel from string from ADS5 S5 string itself is not clear as far as is not known as far as I'm aware. So, and finally, if we move away a bit from string theory and gauge theory, all of this progress in string theory is actually in integrable string sigma models has actually led to a much better understanding of actually the landscape of integrable field theories in 2 dimensions itself. So different communities have contributed to this, but there's been important contributions from the string side. And there are sort of these new classifications involving higher dimensional gauge theories, something I'll come back to in a second, and affine-Godin models. Also important questions about quantization, the relationship between integrability and renormalization, and renormalizability, and how to, and whether you can formulate sort of strongly coupled jewels on the world sheet. Let me, it would also be interesting to look at integrability in more than 2 dimensions, so there's some interesting results in that direction. And then applications beyond mathematical and theoretical physics. So we heard yesterday in the public lecture about various statistical mechanics models. There are a whole bunch of statistical mechanics models that have as part of their description very symmetric sigma models, and it kind of be including supersymmetric sigma models, and it would be interesting to ask all of these deformations we've seen in string theory, do they mean anything, or do they have any counterpart in these statistical mechanics models? So that's my sort of list of kind of directions that I think would be interesting. I just want to finish with 2 things that I've been working on, two directions that I think are interesting, which are related to some of these questions that I've mentioned here. So the first is 4D Chern-Simons. So the landscape of integrable field theories continues to grow. You can try to construct them directly. You can also try to use more general guiding principles. So you can use this ideas of deformations or dualities. But there have been these two sort of systematic frameworks or approaches that have been developed. So affine Godin models and 4D Chern-Simons. I'll briefly explain what 4D Chern-Simons is, but these two are very intimately related. In fact, they're sort of, you can think of them as the Lagrangian and Hamiltonian formalisms of the same system. So this is the action of 4D Chern-Simons. It's a four-dimensional gauge theory. Sigma here is our two-dimensional worldsheet, so that was our cylinder from before. The other two dimensions are given by a CP1. And omega, this omega that sits in front of the action, there, well, you can see it, is a given meromorphic one form on the CP1. And the field A is a G-valued one form on the full 4D space. So to define this theory, it's not actually defined as given. We need to specify what omega is and also specify boundary conditions to make sure the boundary variation vanishes. And then by introducing defects on CP1 and degrees of freedom living on those defects, what we can find is that the theory localizes to give different 2D IFTs. And there are different types of defects. There's what are called order defects. These are quite restrictive. There's disorder defects where we introduce poles and zeros into omega. And then we can also introduce sort of branch cuts that describe models on cosets. So this is a sketch of an example. So I claimed in the previous slide that basically to specify the theory, we specify omega and we specify boundary conditions. That should tell us what our theory is. And for the PCM, this is what omega is. So basically it has two simple zeros at plus or minus I, and it has two double poles at plus or minus 1. And the boundary conditions are that the gauge field should vanish at the double poles. And in this picture, the ideas of deformations and dualities become very intuitive. So to deform, what we can do is we can move these poles, or we can split these poles, we can move them around. So for example, in this picture, I've split the double pole into two simple poles. I've modified the boundary condition, and it's not clear from what I've written, but this boundary condition will reduce back to the PCM boundary condition in the limit where the two poles coincide. On the other hand, dualities tend to correspond to changing the boundary conditions, keeping omega fixed and using different boundary conditions. So this example here is basically going from the PCM to its non-abelian T-dual. And what's nice is that if you split the double pole, you can interpret this as taking you from a rational to a trigonometric model. So we map from the plane, from CP1, and we take our two poles to the ends of our cylinder, and we're just left with a cylinder with a double pole and two simple zeros. And then we can go further, and we can go to elliptic models by gluing the cylinder together. And in principle, I don't, as far as I'm aware, there's not much work on this, but we could even go to higher genus Riemann surfaces. So one fun thing you can do is go lift up to even higher dimensions, and you can construct diamonds of integral models. What you find is that 4D IFTs, so what you find is on this bottom left-hand side, we have 4D Chern-Simons and 2D IFT, and you can lift this up to 6D holomorphic Chern-Simons and 4D IFTs. These 4D IFTs are related to self-dual Yang-Mills and the Ward conjecture. And even now, after many, many years of people coming up with new integral sigma models, these kind of higher dimensional gauge theory constructions are still giving rise to new field theories and relations between them. So there's still much to explore. And the final thing I want to mention, maybe my last 1 plus epsilon minutes, is the ADS3 times S3 T4 superstring. So this is a very nice example. In particular, it has a direct product symmetry group. So we have two copies of PSU 1,1/2. And this direct product structure gives a new freedom. So we can deform copies of the symmetry group independently. And the case where only one copy of PSU 112 is deformed is particularly interesting. In particular, half the global symmetry is preserved. So we only deform one copy and we leave the other copy alone. So if we just look at the S3 part, what we find is that this, if we do the trigonometric deformation, we find the squashed 3-sphere. So that's sketched here. We have J1 squared plus J2 squared plus J3 squared, and then we just deform one of the legs of the current. And let me not go through all the details, but this model ends up having some very nice properties, including supersymmetry, integrability, Weyl invariance, regular curvature, so no singularity, homogeneous fluxes, and a constant dilaton. And in my mind, it's probably the best candidate to find a sort of Q-deformed version of the ADS-CFT correspondence. And then you can even go further and try to do elliptic deformations, and you find that many of these nice properties carry over. The Weyl invariance, the regular curvature, homogeneous fluxes, and constant dilaton. However, supersymmetry and integrability are still an open question. So with that, I would like to just say thank you for listening, and I'm happy to take any questions. Thank you.
Questions?
So this integrable sigma models, some of which you're talking about, are they stable under RGs or what?
So these are, sorry, yes, these are all stable under one loop RG flow. Two loops is a bit more subtle, but for one loop they are all stable under one loop RG flow.
It's.
And this is, so actually there is a very nice picture of this from 4D Chern-Simons. There is a conjecture that basically, if you have your poles and zeros, you can construct various monodromies of your twist function. And so all of your couplings are essentially contained in your twist function. And you can construct various monodromies and any monodromies that are encircling poles will be RG invariant, and then monodromies in between zeros have a very simple RG behavior. But there's a sort of it's still conjectural, and I think there is much to be understood there. But there is a kind of indication that this RG from 4D Chern-Simons, or 4D Chern-Simons, may explain this very nice RG property that all of these integral deformations appear to be stable under RG flow.
More questions?
Hi, Ben. I have a question about 4D Chern-Simons theory. What is known about quantum 4D Chern-Simons theory?
Very little. So, in the case that there are no disorder defects, then I think everything is in principle fine. You can quantize. So there are disorder defects essentially correspond to having zeros in your twist function. And when you have zeros in your twist function, in principle, the theory close to those zeros becomes strongly coupled. And then it's very hard to understand anything about quantization. But away from, if you are talking about order defects, then omega does not have any zeros. And then in principle, you can just use perturbation theory. You can quantize this model, and much has been understood, going back to Costello and Yamazaki and Witten in their papers.
So can you see RTT relation for the lax matrix?
Yeah, so in these cases, these cases correspond to having an ultra-local Poisson bracket, and then
ultra-local.
Oh, yeah. So the order defects corresponds to having ultra-local.
It's basically a spin chain.
And certain very nice sigma models,
right.
Well, which are related. But yeah. So yes. I'm not. Yes. So 4D Chern-Simons with disorder defects is the more interesting case, and understanding quantization there is, it's a big open problem. I don't necessarily think it no, that's not fair. I think it could buy you something in terms of 4D Chern-Simons. I reserve my judgment, but it waits to be seen.
And I suppose 6D Chern-Simons even worse.
Worse. Actually, weirdly better. Some of the zeros Well, it turns out that some of the zeros that come in the 4D Chern-Simons, some of the zeros that are appearing in the 4D Chern-Simons twist function are not there in the 6D. They come from the symmetry reduction. So weirdly, actually, you can say more about the quantization of the 6D holomorphic Chern-Simons than about the 4D Chern-Simons. And there is a poster of Lewis where he can probably tell you more about this than I can. But there is a symmetry reduction in the way. And so I don't think it teaches you necessarily about the quantization of the 4D Chern-Simons and the 2D IFT. So, yeah.
Okay, thanks.
I have a question. If you start from maximally supersymmetric Yang-Mills theory, that's 5 cross 5. So we know there is certain quantity in this theory could be computed using localization. So what happens if you start introducing deformation? What kind of deformation are consistent with localization, and if it's so, what can you compute in those theories?
That's a great question. Honestly, I can't think of anything in that, any work that's been done in that direction. Please correct me if I'm wrong, but it's a very interesting question. I've not thought about it.
Yeah.
A naive question. 6D Chern-Simons is 3D Chern-Simons multiplied by 3 form, or 5D Chern-Simons multiplied by 1 form?
Yeah, so sorry, I've been a bit sloppy. So it's 6D holomorphic Chern-Simons, which is basically a much in the same, well, if I go back to this action, in this case you have a gauge field, a 3,3, so in this, when you lift to 6 dimensions, the omega becomes a 3,0 form, and then you have the normal holomorphic Chern-Simons 3 form, or anti-holomorphic Chern-Simons 3 form, pairing it to get the full.
The model is 1 form multiplied by Chern-Simons, 5-dimensional Chern-Simons. It is not so interesting.
I wouldn't say that. It's something I've not thought about, so I don't have anything to say, but it could be interesting.
Yeah, but just to know if you are aware of, according to this work of Williams, who claim to prove one loop exact beta functions for the Chern-Simons sector, I'm not sure. Do you know how much of this one loop exact arguments can translate to this holomorphic Chern-Simons theory or supersymmetric ones, like in 2D? So these are like 2 different sectors.
So you say there's a proof in the case of...
That's what they claim.
In case of disorder defects or in the case of order?
I think even without defects.
Oh, okay.
Like in regular CS theory, yeah.
Say again?
In regular Chern-Simons.
In regular Chern-Simons, not
this
in...
is what Williams, they talk about.
Not in 4D
yeah,
Chern-Simons.
Yeah,
Sorry. Okay. And then your question... Okay.
And the point is how much of this, if you know, can translate to holomorphic sector. Holomorphic Chern-Simons.
Well, seeing as I'm not aware of that result, I can't, I'm not sure, but I would certainly be interested to discuss. Yeah.
Any other question? Then let's thank Ben again.